Hello. So in this video, we are going to solve one compound or complex circuit. This would be a combination of a series and a parallel circuit, and this will be the last video in our series. So if you look at the circuit at the top here, we have all of the charge going from the positive terminal through the 80 ohm resistor, and then each charge must choose one branch to go down at this branch point. So we have a 50 ohm resistor or a 100 ohm resistor. So since all of the charges must go through the 80 ohm resistor, we say that this resistor is in series, but since the charges have to split at this branch point, we would say that the 100 ohm resistor and 50 ohm resistor are in parallel with each other. Another way you might hear this phrased is that the 80 ohm resistor is in series with the combination of the 150 ohm resistors. So in order to solve these, we have to solve from the inside out. And so what we're doing is a term called collapsing the circuit. And in this example, it's going to be easiest for us to collapse the parallel circuit first. So to do that, we need to review our parallel rules. And we have two resistors, and so to solve that, looking at your equation sheet, we know that 1 over the equivalent resistance in parallel is equal to 1 over one resistor plus 1 over the other resistor. And so I'll put the math up for that. So the parallel branch that we're looking at is 1 over the equivalent resistance for that, 1 over our 100 ohm resistor plus 1 over our 50 ohm resistor. So if you need to review how to solve these problems, you can look in our last video, but you get that the total equivalent resistance for that branch, for the parallel branch, is 33.3 ohms. And so we would rewrite that circuit at this point with an equivalent resistance in the parallel branch. So we're summarizing both of those as one resistor with a resistance of 33.3 ohms. So now we're looking at the circuit, and we're saying that all of the charge must flow this direction through the 80 ohm resistor, and then through the 33.3 ohm resistor, and then back to the other side of the battery. So we still have two resistors in there, and if we want the total equivalent resistance for the circuit, we have to make one more step. And to do that, we use our series adding rules, because both of those are in series. All of the charge must flow through both of them. So our series adding rules, if you need to review those, check out our last video. But series is pretty easy. We just add them all up because all of the charges must hit all of that resistance. So we add up our 80 plus 33.3 ohms, and we get a total equivalent resistance for the entire circuit of 113.3 ohms. So that's useful because then we can find out other parts of the circuit, which I'll show you next. So here we have the same work, and we know that the total equivalent resistance is 113.3 ohms. Let's assume that we have a common wall outlet here. So your potential difference is equal to 120 volts. So that's what our source would be here, our battery. If we want to find the total current coming out of that battery, we use the following equation for Ohm's law. So we know that V equals IR, and if we're looking at the total current here, we have the total voltage equals the total current times the total resistance, which is why it was important for us to solve for the total resistance up here above. So we know the total voltage because that's given by the battery. Usually that's given at the beginning of the problem. And we have our total resistance, which we just solved for. So plugging in those numbers and rearranging, we get our total current leaving the battery to be 1.06 amps. So then when we have the total current through the entire circuit, we can find the voltage drop across the 80 ohm resistor. So at this point we have collapsed the circuit to find the total current and the total resistance. Now we can start breaking it back out to find the voltage drop across any individual resistor. So we can use Ohm's law, V equals IR, like we did in our last video, for many different parts of that circuit. So we know that our 80 ohm resistor is in series, so all of the current must go through here. So the one that we just solved for is the total current leaving the battery. All of that current must go through the 80 ohm resistor. So here's the math for that. We want to find the voltage drop. And we know the voltage drop won't be the total 120 volts, because if it were, then there would be no voltage left to drop over either of these resistors, the 100 or the 50 ohm resistor. So we solved for the total current, and we know that's the current going through the 80 ohm resistor, and we know the resistance, which is given as 80 ohms. So V equals IR for that specific resistor, so watch your subscripts here, multiplying those together, and we get a voltage drop of 84.8 volts. So you can think of this as any charge leaving the positive terminal of the battery has 120 volts to give. That's kind of like its currency. It's going to drop 84.8 of those across this 80 ohm resistor. And then the difference there would be whatever it has left to drop across the 100 ohm resistor or the 50 ohm resistor, because these are in parallel. So it can drop that over either path it takes. You will never get the case where all 120 volts is dropped across this resistor, because it's almost like the charges know that there's more resistance to come, so it has that voltage currency to drop across this one or across that one. So now let's review what we know so far. So we know that our total resistance for the entire circuit is 113.3 ohms, which we use to solve for the total current, because we were given our voltage of 120 volts for this circuit. We also know the voltage drop across the 80 ohm resistor, which is 84.8 volts, and we know the current going through that one. But if you're looking at each of the three variables for all three of these resistors, we have totally solved for this resistor. We know V, we know I, and we know R. And if we look at our other two, we can solve for a V. We don't know it explicitly yet, but I alluded to it in the last slide. We know our resistance, and we also don't know our current. So let's look at the voltage drop so we can nail that down first. And it's important to recognize that these two resistors, the 100 ohm resistor and the 50 ohm resistor, are both in parallel. So whatever the voltage drop is across one of them will be the same as the voltage drop across the other. So looking at our parallel rules, since these are in parallel, we know that the total voltage drop in parallel is equal to the voltage drop across any one individual branch. So it's the same for example, resistor 2 as resistor 3. The voltage drop will be the same. And so in our combined, our complex circuit, we have the total voltage drop in series equal to the voltage drop across resistor number 1 is equal to either the voltage drop across 2 or 3. So like I said, each charge can go through here and drop some of its voltage across this one, and let's pretend it goes through this branch, the first branch here with the 100 ohm resistor. Whatever voltage it has left, whatever that potential is left, it's going to drop that potential across the 100 ohm resistor and then continue on to the battery with 0 volts left. So for that, we know we have a starting voltage of 120 volts. Across the 80 ohm resistor, it's going to lose 84.8 of those volts. And so it's going to drop the difference between those across whatever resistor it chooses. So plugging in your numbers there and solving, we find that all the charge has 35.2 volts each to drop across either the 100 ohm resistor or the 50 ohm resistor. So now that we have, remember if you're keeping track, we have the resistance across each the 100 and the 5 ohm resistors, and now we have solved for the voltage drop across both of those. So we're only missing one variable, so we're just backtracking. We've collapsed the circuit and now we're going the opposite direction. We're expanding the circuit. So the only variable we have left is the current. So here's the work for that. We know that in a parallel circuit we have to add up the current between the two of them. And so we have a parallel branch right here, and so the total current for the whole circuit is going to split between the 100 and 50 ohm resistors. Now it won't split evenly, as we'll find, because there's more resistance on one. So if you were a car driving down the road and there was more resistance or more traffic on one of the roads, there would be fewer cars on that one than on the other one. So combining that with our series circuit current rules, we know that the current through any one individual resistor is going to be the same because the current has to go through all resistors. So in our series rules, we have the current through number 1, which we've already solved for, that's the total current, is equal to the total current going through resistors 2 and 3 for us. So it's going to split for us so that we can solve for the current of the 100 ohm resistor and the current through the 50 ohm resistor. So looking at each one, you rearrange your Ohm's law equation to solve for current. We have our voltage drop across each resistor. So divide those two together, and for our 100 ohm resistor, we get 0.352 amps. That's the current going through the 100 ohm resistor. And then doing the same thing for our 50 ohm resistor, the voltage drop across it divided by the resistance of that resistor, and we get 0.704 amps. And so the last thing we're going to do is combine these together, because when you combine your 100 ohm, the current through your 100 ohm resistor and the current through your 50 ohm resistor, you find that they add to 1.06, which remember is our total current. So going back up to our picture here, we have all of that current leaving this battery, or whatever voltage it is. They're crossing this one, and then all of those charges, all of that current must split. Let me get my cursor back here. Must split between this branch and this branch. And so let's say they split and go over the 50 ohm resistor. They must meet back with all of this charge here and then resume with total current going back to the battery. So both of these branches add to 1.06. And that is how we solve all of the pieces of a compound complex circuit. If you think of each resistor, we now know the resistance, the voltage drop, and the current through each of these three. And we have solved for all parts of a complex circuit.